Hello, everyone. In this my presentation, I will show you a new method for rain detection from the GPM constellation. Then I will use the microwave radiometers orbiting in this constellation. This will offer a new prospect for operational application that we are planning now and a global climatology. The first part of the presentation will focus on the theoretical basis of the method, which is called MWCCH. And in the second part, I will show you some applications and then the conclusions. The microwave cloud classification method was developed before the AIT detector, and it is a method which exploits the perturbation induced at 183 gigahertz from clouds. And then this method calculates sort of perturbation, this PME here, coefficient, which is contained information of kind of clouds, and the combination of this PME compute the scalar MWCC, which is the classifier, formerly the classifier of cloud type. On the bottom right, you can observe the legend. We are able to classify 3 different levels for stratum clouds and the 3 different levels for convection. For example, convection number 3 is linked to the deep convection. Well, the MWCC computational scheme has been improved by a probability-based module for AIT detection. More details can be found in our publication that I will list you at the end of the presentation. A modified sigmoidal function has been assumed for the model for detecting AIT. Here you can observe the formal equation, where you have the first part of this equation strictly depends from the frequency. The frequency is 150, 190 gigahertz. And the second part is the carrying capacity. The combination of these two equations give us the H function, which is the A function. It's only one dependent from the frequencies 150, 157 gigahertz. This is the method MWCC before AIT detection, AIT detector, and then we were able just to identify deep convection in red in this equation here. By implementing the model for AIT detection, we understood that the main core of this storm was related to the storm, very big hailstorm. Maybe this is the biggest hailstorm in story in South Dakota. This is a theoretical distribution of the H function versus the carrying capacity. Then you can see here the different category of hail that we are able to identify. The hail potential is from 0.20 to 0.36. The hail initiation is this range here. The hail means large hail. 0.45, 0.60, and the rest is the detection of the super hail events. Of course, the last part of this distribution, where the curve became asymptotic, is a very rare event. We validate our method on the United States by combining with a matchup data. We use 12 years where satellite data and NOAA hail reports, it's ground observed, hail information has been convolved, and then we got very interesting scores, and this support the robustness of our method. So the method originally developed for MHS sensor and then MCB, which is the predecessor of MHS, has been extended to the whole GPM constellation. In particular, we use all MHS-like instruments, and then ATMS, GMI, and SSMIS. The adjustment procedure formally reconstruct the MHS channel at 157 gigahertz by using the MHS-like sensor. Also here, I says again, more details is in second part of our work. This is listed here. We identify 3 key variables which is also connected to the differences between the MHS and MHS-like instrument, using MHS as a reference instrument. We use the different sampling frequencies, which is the first key variable. The second was the scanning geometry, and the third is the spatial resolution. We create a sort of pair between the reference instrument, MHS, and the MHS-like, in this case, for example, GMI, which is used, this pair here is used for quantify the impact of different spatial resolution, or the second pair, MHS versus SSMIS, has been used for quantify the impact of the different scanning geometry. And then the MHS ATMS, since MHS is the predecessor of ATMS and then are quite similar radiometers, we use this pair for quantify the impact of the different scanning, sampling frequencies. At the end of this work, we extend the frequency domain to the range 150-170 gigahertz, then also exploiting the attitudes of these frequencies to identify aim. The equation has been formalized by this linear regression equation. Equation is the number one here. When you have on the first member the reconstructed frequencies 157 gigahertz of the MHS-like instrument, and on the second part you have a sort of correction terms strictly dependent to the frequency, to the signal in terms of brightness, temperature observed to the reference instruments. So this linear regression equation is applied to the whole MHS-like sensor, just for reconstructing the MHS signal at 157 gigahertz. Then we have the original signal from the MHS at 157 gigahertz and the reconstructed signal at 157 gigahertz from the MHS likes, and then these two contributions feed the original model MWCC-H for detecting aim. The equation one has been specialized for each instrument, and you can see in the left part of the screen the equation, and on the right part of the screen you can observe the list of the correction terms as a function of the observer TB. Of course, for each sensor, a sort of theoretical distribution is a TH proxy diagram has been calculated. A TH curve or diagram is a sort of a slide rule for quickly identifying the L diameter category by crossing the native satellite measurement with the L probability range. This is here an example for ATMS, and the animation can explain better what I told you. If ATMS measure TB close to 220 Kelvin, you have no AL. A signal 140 Kelvin correspond to super AL. Of course, the same for SSMIS and GMI, and of course MHS, which is the reference. A question: why extending MWCC-H for detecting AL to the whole GPM constellation? Well, the reason is maybe better explained from the next slides. By using the whole GPM constellation, we virtually reduce the intrinsic time gap of a polar orbiting satellite. Here you have an example where this sequence of A storm events has been reconstructed from the early morning to the late day. The second example is here. During the last July, you have a reconstruction with the whole constellation of this event with the intensification in the afternoon. And of course, you have also a positive impact on the global application. Just for concluding, this work demonstrated the unprecedented capability of the frequency 150-170 gigahertz in identifying AL clouds. The flexibility of methods led an adjustment, very low-cost adjustment to the whole GPM constellation. And such ongoing works, we are now submitting a paper where the climatology of the Mediterranean basin has been calculated. The global climatology from the GPM area has been calculated, and then we are simulating the impact of our method on the new APS second generation radiometers, means MWS and MWI. This is just a promotional window. It's an open special issue for satellite micro remote sensing from severe storm detection. I will invite you to submit your original paper. This is the two paper mentioned during my presentation. Thanks so much for your attention.